Hello everyone. Today's topic is directed graphical models again and conditional independence relations. This is basically the product rule of probability. If we have v variables assuming absolutely zero independence relations, this is a factorization of this generic. Okay, so look at it carefully, and p of x 1 to v equals p of x1 times p of x2 given x1 into p of x3 given x2 x1, and I can write it several decompositions like this. For example, I can start with x2, then p of x1 given x2, then p of x3 given x1 comma x2, etc. Okay, this expansion is very expensive to do. If you just look on this, if you have let's say k values for each variable x, and you have v of those, then this will require a table of the order of k raised to v. And this is the reason why we study probabilistic graphical models, because we will be asking questions such as, can we actually simplify this conditional distribution accounting for some independent relations? If you really explore given x1 and x1 depends on x2 and x3, can I get value of x2 and x3? If the answer is yes, then we will be able to do factorization that is very efficient. So when you look at probability of x1, we need k numbers to describe it, k square to describe p of x2 given x1, k cube to describe p of x3 given x2 and x1, and k raised to v to basically describe p of xv given x1 to v minus 1. Now, those who study machine learning, if you have a distribution like that and you want to use it, say in the context of a classification problem, there is a lot of tricks you can do so that you don't have to deal with the complexity of k raised to v. And so here is one example. Rather than making tables for each of those conditional probability distributions, what you can do is you can replace them with a multinomial logistic regression model. So each of these distributions are logistic here. So t can go from 1 to v, depends on all the previous values of t. So I try to fit this distribution to some sigmoidal function with an argument of some matrix w times the vector x. This is sort of a nice model. This is a sigmoid function. To fit this probability, you take k components of the argument, and there is a nice model for this conditional probability. For any of them, you don't need a table to describe any of them. Now it comes out that the cost of this model is k times v square, order of k v square. Previously it was k raised to v, and now it is k v square. So it really depends upon v is, but it significantly reduced the cost. However, this model is not very useful, right? Because each of these conditional distributions depends on all previous variables. So you may not be able to use this in the context of classification. So If you want to do predictions and if you want to find marginals account or marginals account for evidence, something like that, then you will not be able to do the algebra using this model. But again, the idea of this model is better than having tables for describing things. Fit some functions, alright. And in this case, you will need to compute this matrix W, and once you have it, then this could be an easy problem to use in the context of classification. So we don't want to do this. What we want is something better. So I'm going to introduce some basic things in probability in case you don't have not you have not seen them. That is relative or marginal conditional independence. So I have these random variables x, y, and z that can be scalar or can be vector. So I can say that x and y are conditionally independent given z when p of x given y comma z is equal to p of x given z. Okay, so if I know z, learning something about y doesn't make any difference when it comes to the value of x. Okay, so this is one way to write the conditional independence of x and x comma y given z. This is important. That is why I say conditional, because there is an argument z there. Now if you use this, you could take this as a definition: p of x comma y given z equal to p of x given y comma z into p of y given z, which is equal to p of x given z into p of y given z. You can use this as a definition when this conditional distribution factorizes like y and z are independent. Sometimes this would be convenient, sometimes the other one, but they are exactly the same thing. We also need to think of this conditional independence relations in terms of sets of variables. So you can write a set x of random variables is independent of y given z for every x in the set x and every y in the set y. For example, say we will see this in graphs. This set of variables is independent of that set of variables, so this basically follows this definition here. And if you get rid of dependence from z, the marginal independence, basically if you take the definition, for example, p of x comma y is p of x into p of y. Okay. So to communicate this message on conditional and marginal independence, given the speed of the car, I am saying that the speeding fine is independent of the type of the car. Conceptually, you understand that if somebody goes in 100 kilometers per hour, then the probability of getting fine is independent of what type of car he drives. Okay, but if you do this marginally, means if the speeding fine is not independent of the type of the car, I mean if you drive a sports car, you have the tendency to drive faster. This forms a trivial argument in the context of directed graphical models is very essential, because you will define the causal relations and independent relations which you can postulate. Another example, which is actually the opposite of this, you have let's say two teams playing some game like basketball. The ability of team A is marginally independent of the ability of the team B. Let's say they are both average teams, so marginally they are independent. If you know the outcome of the game, then you cannot say that conditionally A is independent of B. If A is 1, then we say that the probability of A is higher, which is exactly opposite case to the first example. This is the definition again. What I am going to do here, I am going to write this is the standard way to discuss the hidden Markov and state space model. This is a Markov chain. You can imagine you have some state variables, and if you look at the variables of it with time, so x is the value of the time 1 at 1 time 1, x2 at time 2, and x3 at time 3, etc. So I am using the Markovian assumption here. The value at time t depends on the value of time t1 t minus 1 only. So compare this expression with the previous long expression. So comparing to this, right, the Markovian model is very much simplified because xt does not depend on xt minus 2, xt minus 3, etc. So this model basically assumes independence relations. In particular, given xt minus 1, xt is independent of all the previous values of xt minus x, that is xt minus 1 to etc x1. In this section, I want to introduce a fundamental conditional independence relation for this directed graph. You can see that xv is independent of the non-descendants of xv is independent of the non-descendants of v given its parents. So given the parents, if I know the values of parents, it says that the values of v is independent of the non-descendants. So if you think of the topological order of the non-descendants, will have numbers, but they are basically anything about the values of parents, basically in the order. These are the non-descendants, and so if I know the values of the parents, xv is independent of the non-descendants. I'm not proving or anything like that at this point, just want to visualize as to what this means, because once you have this, the decomposition of the probability to find on this graph will be very easy to simplify. So we will be able to take the advantage of this relation. So in principle, we show that any distribution that factorizes this graph satisfies this relation, and for any distribution in the graph, this relation is also correct. So both ways, this will be a correct argument. So using this relation, we will be able to show that the factorization of the joint probability on a directed graph is written as the product over all nodes of the graph of the conditional probability of xi's, the variables in node I, given the parents of I. This is a great decomposition if you think about it, right? So you know there is a function, in this case a conditional probability corresponding to each node, and this function is a conditional probability of xi given its parents. So any distribution that factorizes this graph because of this independent relation that we introduce sort of identical as a conclusion and a fundamental property of directed graph. The joint distribution factorizes over the loads, and these factors functions are the conditional probabilities of exercise given its parents. What we had was this complicated factorization from the product rule. Here we have only the parents, the children and the co-parents and the non-descendants. Everything else was coming there, but because of this independence relations, the only factor which is given by xi is given its parents. The only factor which is given by xi uh, and given the parents of node I. Here I am taking a directed graph with 5 variables. The first equation writes the product rule with no independent assumptions, and that is I am assuming nothing, and then I am applying this equation that says this distribution is factorized this way, and I am writing it as the probability of x1 because x1 has no parents, the probability of x2 given x1 uh, because x2 is the only parent of x1, x4 given 2 and 3, and x4 given 2 and 3, and x5 given 3. So immediately you can say that the independent relations that are being used here, effectively what I am saying is that this probability is equal to that. So given x3 and x5 independent of what? I mean, looking at these two equations here, given x3 and x5 is independent of, given x3, x5 is independent of x1, 2 and 4, right? Like that, given x2 and x3, x4 is independent of x1, etc. So you may say, how will I know? I give a graph like that. That is, in a general graph, how will I know this independent relation? Just look at this equation. If each of these variable takes k values, almost let's say discrete values, and we have v of those, the cost basically is in general v to the power of k. But right now the cost is if we have v of these terms, it's v times what is the cost of this. Let the parents number of parents be f, then the cost will be k raised to f, and total cost is v to the power of v times k to the power f. Okay, so we will see actually much more general equation even for the sort of undirected graph. Right now, in the context of this, let's say f is the number of parents and k to the power f is to describe this. Hence, the cost is v times k to the power f. In principle, actually, if somebody can say that the power f plus 1, since each of the parents and this also takes k values. This is sort of 5 random variables. You can see different orders which will be the graph you will like to use. They're all the same, right? So, but which one is with minimal cost? The true thing is the left one is preferable because the left one is having less number of edges, right? So that is less edges means more number of independent relations, and this is what we are interested in. Something very complicated that we don't like, right? So it says here it is the absence of edges basically is important, because this indicates conditional independent relations. Okay, I'm going to highlight the proof of the decomposition on the directed graphs. Actually, the proof is trivial. So let's assume the following: associated with every node in the graph and its parents, we assign some arbitrary potential function. I call it ft xt x parents of t. This is like a local potential associated with a node that only involves x and its parents, and we assume f x t x parents greater than or equal to 0, and when we sum over xt, that is equal to 1. By looking at this assumption, you may have thought that you can show that this function is a probability. So when we consider all the family of the probability distributions, that they are the product of this local potentials. Okay, and this theorem basically says this is first normalized. So when we sum over all the values of all the variables x1 to t equal to 1, which is really nice. So obviously each individual are normalized, and more importantly, this decomposition here, you can show that the conditional of xt given its parents is actually this function here. So basically, if you decompose the joint distribution in terms of such that it involves only xt and its parents, it comes out that this function is the conditional distribution, which is what I told you need to remember. Okay. The first part of the theorem was that if it's this function is individually normalized, then its product will also be normalized. So if you take this the product of this all of these functions, and we sum on all possible values of x1 to xt, this will come to 1. And what I have done is I basically I split this summation on x1 only, summation on x1, then x2, and then x3 etc., then xt minus 1 and xt etc. So when you take the summation, the individual summation here, you immediately notice that this is equal to 1, this is equal to 1, this is equal to 1 etc. Each of this summation will be equal to 1, and the theorem is proved. Okay, so this is basically actually this sort of calculations that is going to make the operations of graphical models extremely efficient. The second part basically demonstrates that these functions are indeed conditional distributions xt given x parents of xt. This proof is also trivial. So what I have done is I want to prove that this probability is this this probability is this function, like that. I postulate this, use any function like that, take the product form of take all the products and form a joint distribution. What I'm going to do here is show that this is equal to that. So what I do is I write this as the joint x k plus 1 and the parents of k plus 1 divided by the parents of k plus 1. Calculate the numerator and denominator using the appropriate marginalization and decomposition of the joint probabilities distribution. So look at either the numerator or denominator and tell what is going on there. Okay, I am going to prove this by induction. At t equal to 1, there is no parents, so the proof is very obvious, and we have shown this is true for we have shown that this equal to true for t equal to 2 to k. Then we need to prove that it is true for t equal to k plus 1. So when I write the decomposition of the joint probability distribution, that is counted from 1 to k, these are the conditional distributions, because that are part of my induction, and below ones are the factors. So this is that is in step 2 is to get this marginal of k plus 1 and the parents of k plus 1. I have to sum over all the other variables. What I mean is I have to sum on k plus 2 to up to v, and because I have a topological ordering that doesn't include the parents of k plus 1 which are before k plus 1, so I don't have to worry about the parents. And this one I don't sum on x k plus 1 on the or the parents. From here to there I have to sum over all the previous nodes from 1 to k except the parents of k plus 1, which will possibly might be k or either before k plus 1. Here I am pushing the summation inside, and I have accounted the potential up to k according to my induction argument. They are really the conditional distributions, and then I have this summation. They are all the factors. So it comes out that if you do this and you do this, so the denominator you have to sum on xk plus 1, because there is no xk plus 1 here. So the whole summation in the numerator and the denominator it cancels, and this factorization by definition is 1, because these functions are normalized. So what you get is this conditional distribution is equal to my factor f k plus 1. So basically what we said was we can decompose joint probability distributions in terms of its conditionals.